Here we go. All right, so everything that we're going to do in this section is a culmination of the skills and concepts that we've been talking about, previously, and pretty much even all the way back to like arithmetic, algebra 1, putting it all together to come up with the graph of a rational function, right? We've already tested over rational functions. That's when y'all found holes and VAs, but we never graphed them, okay? We get to do that in this section. And if you like working puzzles or don't like working puzzles, you're going to find this section interesting or not interesting. One of the two. Okay. So either way, we're doing it, right? Yeah. Yeah. All right. So first of all, what the heck is a rational function? Well, the key word is ratio, right? A rational function is a ratio of two polynomials. Okay. Essentially, it's a polynomial over a polynomial. And what the heck is a polynomial? Well, a polynomial, as you know, I've experienced with, is something like x squared or x cubed or even x or even a constant. A polynomial has exponents that are not fractions, not negative numbers. So including 0, that would be like a constant, 1, 2, 3, 4, 5, 6, 7. So really nice exponents, okay? So if we have one over the other, we have a rational function. All right, so what we're doing on example 1 is we're going to sketch the graph of each function. And it says to identify, blah, 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 blah. So here we go. I'm going to talk you through it. It might take the whole period to do this one problem. We'll see. Okay. We'll see. First thing you do when you encounter a problem is introduce yourself. Is it a little warm in here? I thought so earlier. Yeah. Oh, you want to go get it? Yeah. Just take the candy cane. All right. So you introduce yourself, right? Yo, what's up, little R? My name is Mr. Corpy, and I'm here to graph you. Right? He's like, I was hoping you would. Right? I've been waiting for you, driver. It's totally platonic. The function's name is little r. That's its first name. You could call it little r of x, right? That would be its first and last name. Either one. All right, now that you've introduced yourself, the first thing that you want to find about this function is its domain. Always domain first, okay? You don't want to be talking about a function where it doesn't exist. Are you already trying to graph it on your calculator? No, that's like watching the end of a movie before you watch the beginning of the movie, okay? Or listening to a punchline on a joke without hearing the setup. It's better if you do it this way, but we'll get to the graph, okay? I mean, I'm not going to stop you, but we want to find the domain, right? We want to find the domain because we don't want to talk about functions where they don't exist, and we want to know where they don't exist. So remember division by 0, square roots of a negative, all that stuff. There's no radicals here, but we do have a denominator with a variable. Now, when we first learned to do it, we went off to the side and I had you say not equal 0, but that was just to get you used to thinking about denominator can't be 0. We don't have to show all that work now, okay? Once we set it equal to 0, how did we find the values that didn't work? What did we do with that quadratic? Looking for, Teresa went to get her watch. Okay, when she comes back. Yeah. Okay, cool. Yeah. We factored it, didn't we? We factored it. So that's what we're going to do. Now that we know we want to find the domain, we're going to go ahead and factor the function completely. Okay, so directly underneath there, we're going to still call it r of x. Look at the numerator. Does the numerator factor at all? Common factors, anything? No. If you factor out a 5, you're going to get a 21/5 in the second term. Ooh, yucky, gross. It's a prime linear factor, so it's already good, okay? The bottom is a factorable quadratic. And remember, we learned how to factor, so you could set up your two little shells. It's going to be x plus 5 times x plus 5, right? Y'all can work on that. Some of y'all are doing that. Fantastic. Now, when you get x plus 5 times x plus 5, we can actually write that condensed as x plus 5 squared. So I'm going to skip the step that y'all are showing. Don't erase it. Just underneath there, put this step. Don't erase your progress. That's your work, okay? Yeah. Just write it underneath where we have this. Yeah, there you go. And even use a different flavor. That's good. All right. Now, once we have it factored, it's super easy just to tell what value, in this case, value, makes the denominator 0. What is it? -5. Very good. So now we go to the domain D sub R colon. It's the set of all x such that x is not equal to -5. Awesome. Awesome. Okay. We found the domain. Now here's what's cool about finding the domain first. It naturally sets up your next question, or it should, right? Because if the graph lives to the left of -5 and to the right of -5, then that means x equals -5 interrupts the flow of the graph and therefore is a discontinuity. Now, unless it's a piecewise function, normally it's not going to be a jump discontinuity. So, as we learned and tested over on the previous exam, it's going to be either a what or a what? What? A VA or a hole, right? At x equals -5, we have either a VA or a hole. Is it possible to tell from this stage with the information we have here? Not just yes, but yes, yes. Well, no, just yes, yes. No, no, well, or yeah, or two yes, whatever. And the reason I say yes twice, or we can say absolutely yes and absolutely yes, because there's two ways to tell. That's why I'm doing yes, yes. The first way to tell is this, right? What is the proper name for a vertical asymptote? A non-removable infinite discontinuity. Non-removable, okay? So remember, if the factor that causes a 0 in the bottom is non-removable from the equation, that is, you cannot remove it, it doesn't divide out, it's going to be that non-removable vertical asymptote. So guess what we have at x equals -5? A VA. Good. That's the first way to tell. That's the yes. The second way to tell is direct substitution, right? -5 is the taboo value, but if you plug it in when no one's looking, right? You get a -25 plus 21, you get a -4 over 0. Remember, non-zero over 0. Non-zero over 0 means what? Vertical asymptote. Non-zero over 0 means vertical asymptote. It's some type of infinity, okay? What does 0 over 0 mean? Whole, right? But non-zero over 0 means VA. So there's two ways to tell. Did you find your watch? Okay, but now you're missing your ID. I don't see. We're supposed to all be wearing IDs. Oh, what is she doing with your ID? Oh my goodness. Oh my goodness. Oh, you are a mess. Oh, look what just fell out of my America suit. Right? Yeah. Yeah. How about that? Yeah. Only in America. So, okay. Now, in a complete sentence, get in the habit of writing in a complete sentence. R has a VA spine at, and remember, it's x equals. Vertical lines are x equals because the y values can be anything up and down as long as x is at that single point or single location. All right. Write in a complete sentence. What we have going here on the left side is not bench work. No, no. It is actually just an accumulation of things that we are discovering about our function that are going to help us graph it ultimately. Oh, yeah. I mean, we've learned more than just this, right? We could have learned this in one day. We've been here for like, what, 3 weeks already? Oh, I don't know. At least 3 weeks. That's why I heard someone say the other day, hey, Caesar's been dead for at least 70 years, right? Yeah, at least. And I'm like, you're not wrong there, buddy. Hey, now that we know that the function has a vertical asymptote at -5, and that's the only discontinuity, since we're trying to sketch this puppy, speaking of puppies, today's National Cat Day, everybody. National Cat Day. Meow. Okay. Let's come down here above this part C, and let's go ahead and start getting a graph going. And as we find more and more information about the function, we'll add it to our graph, right? So give yourself a y-axis, snap. Give yourself an x-axis, snap. Oh, snap, it wasn't horizontal. There we go. Do it again. Okay, so there's my x and y axis. Now, the important part, pick a flavor for your graph. Strawberry? Banana doesn't show it. Yellow doesn't show up very well. Mustard it is. Mustard. Mustard. Yeah, mustard ice cream. You ever had it? Me neither. Okay. 1, 2, 3, 4, 5. There's -5. Can y'all see that okay? All right. No. Now, here's what's cool. To graph my vertical asymptote, I'm switching to thick mustard, and I'm also switching to dashed mustard. Because, you know, dashed is the Shakespearean way to say dashed, by the way. It's kind of fun. Dashed. Dashed through the snow. No, it isn't. It's pretty close, right? All right, there we go. Now what I'm going to do is switch back. I'm switching back, and here's what I'm going to do. Because I've obscured my -5 on the axes, I'm going to label it down below. I'm going to label it down below. I'm switching to burnt orange. I don't think the mustard shows up that well. Oh, okay. All right. All right. So anyway, there we go. Now look, we have a vertical asymptote. So I know the graph lives to the left and to the right. Cool. Is that enough to complete our sketch? No, we need more info. Need more info. Need more info. So here we go. The sequence was find the domain always first. Once you find the domain, that gives you the discontinuities. Once you have your discontinuities, it naturally lends itself to finding the discontinuities, holes or VAs, okay? Now, since we have found a VA, you're like, oh, asymptotes. Are there other asymptotes besides the one single vertical discontinuity type? Yes. And what are they? Horizontal asymptotes. And they are an asymptote that describes the what of the graph? The end behavior. The end behavior. End behavior. There is no stop on end behavior. It goes, yeah, that's true. That's why I didn't do it. Abraham Lincoln. Okay, well, how about this? What are the two Abraham Lincoln? Great ideas, right? What are the two limits that we use to analyze the end behavior? The limit as x goes to negative infinity and positive infinity. Okay, let's do that. Okay, let's do that. Abe, I would like to get a single picture with you later on because I love Abraham Lincoln. My whole office is like all Abraham Lincoln, believe it or not. Oh, do you? Yeah, okay. He is honest.
Can I get a picture? Is that okay?
All right, sweet. Okay, so I'm expecting to see this. When you're looking at your end behavior, I'm going to expect to see these two limits. Now, for analyzing end behavior, we have two different versions of the function. We have the top expanded version and the bottom factored version. Which one is better for finding end behavior, the top or bottom? The top, because it is not factored, right? So remember to find end behavior as x goes to the infinity for large values of x. All we got to do is look at the leading terms, okay? So terms are non-factored. They're not always in front, are they? But they are always the largest exponent. In this case, they are in the front. So I got 5x to the first over 1x squared. Who grows faster for large x or x squared? X squared. So anytime the denominator grows faster than the top, anytime the bottom grows faster than the top, your ratios are always going to go to what? 0 every single time. And so the answer to this is 0 and the answer to this is 0. Yeah. And now, naturally, it follows from the definition that anytime one of these two end behavior limits is a finite y value, we have a what at y equals that finite y value. An HA, also known as a ha. Good. R as a ha at y equals. Y equals is the horizontal line. Complete sentence. R or R of X has a, not there is, right? R has a. Hey, let's graph that. Come down here, switch to thicker, switch to dotted line. Y equals 0 is the x-axis. So let's, whoa, I'm in purple. Whoop, didn't mean that. Back to mustard.
You should do like relish.
There we go.
No, not relish, do avocado.
Now I'm coming back to normal, flared writing. And again, I'm going to label this as y equals 0. Okay. Now here's what's cool. They are not only the natural things to graph when you're walking through the sequence of information gathering, but at any point when you're sketching a function, if there are asymptotes, you want to always draw them first. Never not first. You know why? They become literally guidelines for your graph. Literally, right? They're like gravity. As you get closer to these, it's very predictable. Like as I get closer to -5 from the left, I'm either going to go up or down forever. As I go out to the left, I'm going to approach 0, right? So I've kind of created 4 quadrants. And most of the time, your graph will live either above or below on either side. But not always. Can a graph cross its horizontal asymptote? It can, right? It doesn't always. Not all functions do. But it's not a discontinuity. Can a graph cross its vertical asymptote? No, never. Okay. So now what else can we do? I don't think we have enough information. So now we're at the point where we're like, we need points, right? I need a couple of points to help guide me. Now, when you were in Algebra 1 and you first learned to graph functions, your teacher told you to make a T-chart, right? And you would have a column for X and a column for Y. Did you not do T-charts? Like this, you did X and Y, and you went like -3, -2, -1, 0, 1, 2, 3, and you had Y equals 3x plus 1, and you would plug them in and generate your Y values. Remember that? Yeah. In other words, you wouldn't pick random values of X, but you would independently choose systematic values of X and plug them into your function to generate the Y value. And once you did that, you would have a set of ordered pairs. And once you have a set of ordered pairs, you can plot them on the X and Y axis. And if you did that enough times, you would have points that you could then connect the dots, right? That system still works, but that's kind of like our method of last resort. That's kind of like trying to solve an equation by guess and check. It's not the most efficient way to do that. It's a good way to start, right? But it's not where we're at. Now, that's not to say that we don't want to plug in X values. We just want to be judicious about the X values we choose. So what is the easiest value of X to plug into any function if it's in the domain? 7.3? 1 is not bad. 1 is easy, but there's an easier number. 0. 0 is the easiest number to plug in. And 0 is not only easy, it's important because any coordinate that starts with 0, 0, 5, 0, -3 is going to live where? On the y-axis. That's your y-intercept. So it's doubly cool, right? He's easy and he's the y-intercept. So let's go ahead and find the y-intercept. Here's how we do it. We're going to label our intentions, okay? So I'm going to put y-int colon. When you do something like that, colon, you're telling the person that's looking at your work, whether it's me or your parents or Santa Claus, whatever, what you're doing. You're labeling your intention. You're helping people navigate through your work. Remember, the goal is communication, not just results. Now, the best way, the surefire way to communicate to the initiates, people that know math, that you're finding the y-intercept, that is that you're plugging a 0 in for X into the function R is what? How do we show that we're plugging in a 0 for X into the function R? R of 0. Thank you. Boom. That is super important. Okay. Anytime you go from like R of X to R of 0, you need to show that on both sides. Okay. So R of 0 equals. Now, you could plug a 0 into either one of these two versions of R, but really it's a little easier if you plug into which one? The bottom is not bad, but the top is a little easier. Okay. In general, the factored version is not bad, but you might end up with several numbers that you have to then multiply together. The top, the expanded version, is easy because every term with an x, when you plug in a 0, goes to what? 0. So the answer to R of 0 is what's left when you cover up all the x terms? 21/25. Yeah, it's staring at you in the face. Hi, here I am. Can I go on the graph? Well, it's okay. It's not that bad. 21/25. Okay. 21/20. Hey, I have a point. Let's plot it. Now, you can leave it as R of 0 equals 21/25 because the beauty of function notation is you see the input and the output. But I grew up plotting points. You remember those worksheets when you're first learning the coordinate plane? It was just a whole sheet of coordinates and you plotted them and then you connected the dots and at the end it was like a pumpkin. Yeah, and then you colored it. It was like, it's a black cat, right? We grow up plotting points. So I still prefer to see something like that, especially when I'm expected to graph it. I like to see it as an ordered pair. It's just my preference, okay? Although it's not needed, I like that. Now I can plot that point with confidence. So let's come down here, go back to my mustard color. I'm gonna put one right here. I'm gonna make the Y scale a little bigger than the X scale. The two scales don't have to match each other, but you do have to be consistent on each individual axis, okay? Now 21/25 should be where in relation to the halfway point between 0 and 1? Above or below? Here's 1/2 right here. 21/25 is above or below it? Above, right? Because halfway would be 12.5/25. So what I'm going to do is I'm going to put a purple mustard stain right there, just below 1. And purple. Let me take my glasses off. Oh yeah, it's mustard color, not purple. Sorry, my bad. I said purple. I don't know why I said purple. They did, like, every once in a while, like they'll make like purple mustard or green ketchup, you know, for holidays. It's just food coloring, you know. Yeah, it's just different colored corn syrup. All right, so maybe. All right, now here's the next thing we're going to do. The other intercept that's important. There can only be one y-intercept, but there could be several x-intercepts. Now here's the deal with x-intercepts. They're not always easy to find. They are meaningful values though, because that's where the graph changes from positive to negative or negative to positive, but they're not always easy to find, okay? How do I find an x-intercept? If y-intercepts are when x equals 0, x-intercepts then are when y equals 0. And you know what another name for y is in this problem? R of x. Yeah, so R of x equals 0. That would earn a check on a test. You always have to show me the equations you're solving. Now, here's what we do. We come up here, R of x equals 0. Look at R of x, it's a fraction, right? A fraction is equal to 0 when the what is 0? Top or bottom? Top, good. We talked about that earlier. We don't like set it up and multiply both sides by x plus 5 squared. Ooh, we lose information. Rather, we say a fraction is equal to 0 when the numerator is 0. 0 divided by 5 is 0. 0 divided by negative 3 is 0. So here's what we do. We say R of x equals 0 when 5x plus 21 equals 0. It's a consequence of that theorem. The fraction is equal to 0 when the numerator is 0. Okay, now we have a linear equation that we can solve. Take as many steps as you need. I get x equals negative 21/5. Another fantastic number. All right. Now, negative 21/5 is a beautiful number. It's a simplified rational number. But if we're going to plot it on the x-axis, it might be useful to know what that kind of is approximately as a decimal, right? It's okay if you just know it falls between which two integers. It's negative what point something? Negative 4 point something, right? So it goes between negative 4 and negative 5. Now, you could go off to the side and do 21 divided by 5 and get the value, or it's a little bit easier, I think, if you just multiply by 2 over 2, you get negative 42/10, which is negative 4.2. So there's a couple ways to do that. Now, I like it as an ordered pair, right? So I'm going to say, hey, that's negative 4.2, comma, 0, or negative 21/5, 0. You could leave it as negative 21/5. Don't think that you have to put it as a decimal, but you do have to make it land between -4 and -5. So back to my mustard color, I'm going to put a mustard stain right there. Here's -4, right? Putting a mustard stain just to the left of that. Now look what I have there. Look at what I have. That's the only x-intercept that this graph has. Do you think as I approach -5 from the right-hand side, do you think my y values are increasing to positive infinity or decreasing to negative infinity? All right, is this passing through here going up or down? I would think down, right? Why would you think down? Because of this guy here? Right. To go from this point here to this point here, it would have to be kind of decreasing, right? Oh, unless it did something silly like this, right? But it doesn't do that because sometimes the evidence is not what's there, rather it's what is not there. If this is what the graph looked like, we would see a what here? Another x-intercept. Do we have another x-intercept? No. So the absence of an x-intercept tells us that it can't do that. So it has to do this. It has to go to negative infinity. Now, do you think it actually just goes through that point like that? Maybe, but it probably does more of a natural thing, right? It probably rises above 1 and comes back down and hits that. And then because of the end behavior, it more than likely does this. Okay. That is what the graph actually looks like, I believe. I'm just guessing based upon our mathematical evidence. I mean, what else could it do, right? It could go up higher. It certainly could go up higher, but I do know that it's continuous everywhere except -5. So if it goes up higher, that's fine. It still has to come back down, pass through 0, 1, and then approach 0, okay? Now, here's the deal. If we knew a little bit more math, we could find this y value. That's a very important y value, right? We call that the local max. Y'all studied that in algebra 2. If I knew that y value, I guess it would be over here. If I knew that y value, I would know how high to draw it, right? Is the high value at 0, 1? Does it actually peak at the y-intercept? Does it go up a little higher and come back down? Or does it go up like crazy high like that and come back down? That's what you were saying. Unfortunately, without calculus or a calculator, we can't find that. And since we're not from the future, we don't know how to do that. But calculus gives you the ability to find this value of x. We call this value of x a critical value. And it's pretty easy to find in calculus. Okay. Once you know this value, then you can plug that value back into the function and get the y value there. And that would tell you how high to draw it. And it would be a meaningful value because it is the local maximum. Okay, it is the local maximum. Now, here's what else calculus would help us to do. Watch this. If you come in like this, notice this graph is curving downward like a frown, yeah? Concave down like a frown. We look at the curvature of the graph. We call this part of the graph concave down like a frown. Curvature is another aspect of the graph that we look at in calculus, okay? Curvature. That part is concave down. We call the curvature concavity. In science class, you have concave lenses, convex lenses. Okay, it depends on which side the observer's on. In calculus or in math, we don't say convex. We just say concave up like a cup or concave down like a frown. So somewhere, I don't know if it's at the y-intercept or not. It looks like it might be, but somewhere it changes from concave down like a frown to concave up like a cup. Like a cup, or it doesn't rhyme, but it goes with the analogy, smile. Any part of a cup is turned upwards, right? It holds water. But so you can think of any part of a frown is concave down, and any part of a smile is concave up. This value right here, where the curvature or the concavity changes, is called the inflection point. The concavity changes. So when someone's voice inflects, their voice changes. That's what inflect means. So the inflection point is where what changes? The concavity. And concavity is the curvature. Now that point we could also find with calculus, believe it or not. So we could actually get a much more accurate graph if we were interested, if we knew a little bit more math. But we're on that road to learning that math, right? The high point and where the curvature changes. The curvature change is a very important point in statistics, because if you've ever looked at like the standard normal curve, the bell curve, right? It's called the bell curve. You know, the way that works is like the population mean is called mu. Most of the population lives there. And if you've had statistics, Kilford talks about it as well. About 68% of the population lives in this region. We call this distance the standard deviation. Okay. And guess where the standard deviation falls? The first standard deviation, it falls at the inflection point of the standard normal curve. Pretty cool. It goes from concave up like a cup to concave down like a frown, back to concave up like a cup. So in statistics, when you're trying to make predictions, probabilities, what's the meaningfulness of some study that we did, right? Do women actually talk more than men, right? Do teenagers act? There was a study. My daughter's I help her with her stat homework. That was one of the case studies I helped her with. Do women actually talk more than men? And you know what? It came out when we got to the end of the problem. Although in the study, the 10 women that they had, which is a small sample size, did use more words than the men, it came out to be statistically insignificant. There was no statistical evidence that in general, women talk more than men. So there you go. There you go. The question then said, what are some of the consequences of the finding? And I was like, well, men are going to get frustrated now because they can't say that women talk more than men. I didn't know if that's what the professor meant, right? Sometimes men use it as an excuse. Ah, my wife, she just won't shut up. She talks more than I do. No, in general, she doesn't, sir. No, can't say that anymore. Anyway, statistics. It's like the mathematics of common sense, right? You're trying to predict with confidence, and it comes down to the standard deviation, which is the inflection point. So anyway, back to this right here. We're left with what the graph looks like to the left of -5. Now, again, because there's no additional x-intercept, it has to either live above or below. It has to live either above or below. Here's where we now have to say, how can I determine if it lives above 0 or below 0 to the left of -5? Knowing that a piece of information is critical for us getting off this island. We're running low on food. We're running low on water. We need to know if it lives above or below to get off the island. Our lives depend on it. What are we going to do to determine if it lives above or below? Are we all doomed? No. Help me, someone. I'm getting thirstier as we speak. And there's no water to drink. No, we're on the island. No, I'm not going to do that. I just want to know if to the left of -5, my function values are positive or negative. That's all we need to know. How can we figure that out? Plug what in?
0.
No, 0's over here. I already know it's. Oh, thank you, our savior. We're going to get off the island. We're going to get off the island. Tex had a solution. Plug in a -6 or a -7. That's a judicious choice of an x value, yeah? All right, so let's come up here. R of 6, -6, R of -6. I'm going to plug it into the factored version. I'm going to get a -30 plus 21 all over a -1 squared. Now notice I did work left to right. So as I simplify now, I work down line, I line up the equal sign. That's -9 over 1, which is -9. If I wanted that as an ordered pair, that would be -6, -9. But you know what? I don't care so much that it's -9, so much as that it's what? The fact that it's negative means that it lives where? Above or below? Below. We're going to get off the island. We're going to get off the island. Uh-oh, I'm out of mustard. I can't draw it. Drink your pee. Same color. Nice. Yeah. So there's what the graph looks like. The graph looks like that. And once we have the graph, I can ask you all kinds of questions. Unfortunately, I can't ask you for the range of this function because it requires us to go from negative infinity up to the local max value, which we don't know. Okay. But I can ask you what's the general limit as we approach -5. Negative infinity, verdad? Sí. Because it goes down to negative infinity on dos lados, right? On both sides. So we can say it's negative infinity. Very good. All right. Now, let's see how the calculator graphs this puppy cat dude. All right. Puppy monkey baby, puppy monkey baby. Oh, yeah, that's right, for the Super Bowl commercial. Okay. There it is. Let's compare. The graph on the left is the calculator's poor interpretation. On the right, it's ours. Whose is better? Ours. Ours. No, Abe. I cannot tell a lie. Abraham Lincoln once said when he was accused of being like a double-crossing liar, he said, if I were two-faced, do you think I'd wear this one? I just touched Carter's nose. All right. So there you go. How fun was it? How fun was that graphing that? And look, in the end, look how pretty it is. It's so exciting to graph with Notability. If you're listening, Notability, we love you. Because before I had to use it on the board with dry erase markers, and my straight lines were all crooked, you know, and then the dry erase markers were like dry, which a new dry erase marker is actually wet. Okay. But when it dries, you can erase it. So it should be not like a dry erase marker. It should be like a wet write marker. That's if, yeah. They have to be juicy to be able to write.
Juicy marker.
Juicy marker. Okay. Anyway, and then before that, I had to use chalk. And there was only two colors of chalk, white and off-white. No, there was yellow chalk.
You have to hold it loosely and then it bounces.
Oh, yeah, you can get that sound. And then you can do your nails too. Yeah, and then you had to erase it and like you're inhaling chalk dust, which you never got heartburn, but then you got like black lung disease, right? Pneumona ultramicroscopic silicovolcanioniosis, right? Boom, yeah, baby. So anyway, now we have Notability and it's healthy, right? Look, you can breathe it in and it won't affect your lungs. It's all colorful. We can make straight lines. And I lost my connection. Hey, that's all I wanted to do for today was just that one example. Y'all were great, captive audience. Thank you. Thank you. Thank you.